Hello and welcome to EduNova's practical session on the verification of the loss of combination of resistances using a meter bridge.
The aim of this experiment is to verify the loss of combination of resistance in series and in parallel using a meter bridge. The apparatus used in this experiment are a meter bridge, battery eliminator, a galvanometer, a resistance box, a jockey, two resistance wires, connecting wires, and a one-way key. If two wires of resistance R1 and R2 are connected side by side in this way, then they are said to be connected in series. If the same two wires are connected in this way, such that the ends of the first wire are connected to the corresponding ends of the second wire, then they are said to be connected in parallel. The aim of this experiment is to verify series combination of resistance Rs using a meter bridge with theoretical value of Rs, and to verify parallel combination of resistance Rp using a meter bridge with theoretical value of Rp. To do so, we find the resistance of the first wire R1 and the second wire R2. Theoretical value of series combination of resistance R1 and R2 can be calculated using the formula Rs is equal to R1 plus R2. Now, let us find the value of Rs using a meter bridge. Connect the wires R1 and R2 in series and fix it in the right gap of the meter bridge. As usual, switch on the battery, remove 7 ohm resistance from the resistance box and insert the plug key. Now, touch the jockey at different points on the meter bridge wire till the galvanometer shows zero deflection. As you can see, the galvanometer shows null deflection. Let's say the balancing length is x centimeters. Note this value under length AD, L centimeter. Calculate length DC and unknown resistance R. Similarly, repeat the same procedure to find the balancing length for 10 ohm, 12 ohm and 14 ohms respectively. Calculate the mean resistance Rs, which is the experimental series combination of resistances. Now, connect the two wires in parallel combination and fix it in the right gap of the meter bridge. Switch on the battery, remove 7 ohm from the resistance box, insert the plug key and find the balancing length. Now, touch the jockey at different points on the meter bridge wire till the galvanometer shows zero deflection. Let us say the balancing length is y centimeters. Note this value in the observation table under length AD. Similarly, repeat the same procedure to find the balancing lengths for 10 ohm, 12 ohm and 14 ohms respectively. Calculate the mean resistance Rp, which is the experimental parallel combination of resistances. Compare the theoretical values of Rs and Rp with the corresponding experimental values. If theoretical value Rs, R1 plus R2 is approximately the experimental value of Rs, and theoretical value Rp, R1 R2 by R1 plus R2 is approximately the experimental value of Rp, then loss of combination of resistances in series and parallel are verified.
Let me demonstrate these steps quickly for you. As usual, I will start with the positive terminal of the battery, since the current starts from the positive terminal of the battery. So, I will connect the positive terminal of the battery to left end of the meter bridge wire. So now, the left end of the meter bridge wire has become the high potential point. Next, I will connect the negative terminal of the battery to one end of the key. The other end of the key I will connect to the right end of the meter bridge wire. As a result, the right end of the meter bridge wire will become the low potential point. Now I'll connect the resistance box to the left gap in the meter bridge. Then I'll connect the resistance wire R1 to the right gap of the meter bridge. Here you need to ensure that the wire does not touch itself anywhere, because then it would short circuit itself and the resistance value would change. So make sure it's not short circuiting anywhere. Now finally, I'll connect the positive terminal of the galvanometer to the center strip of the meter bridge and the negative terminal of the galvanometer to the jockey. Let me summarize the connections for you once again. The positive terminal of the battery eliminator is connected to the left end of the meter bridge and the negative terminal of the battery eliminator is connected to the right end of the meter bridge through the plug key. The resistance box is connected to the left gap of the meter bridge and the resistance wire R1 is connected to the right gap of the meter bridge. The positive terminal of the galvanometer is connected to the center strip of the meter bridge and the negative terminal of the galvanometer is connected to the jockey. Let's take 7 ohms in the resistance box. Switch on the power supply and insert the plug in the key. When I tap the jockey gently at the left end of the meter bridge wire, I expect the galvanometer needle to deflect towards left. And it does. When I tap the jockey gently at the right end of the meter bridge wire, I expect the galvanometer needle to deflect towards right. And it does. So our connections are error-free. To find the mean resistance of the first wire R1, I need to find the balancing lengths for 3 different values of resistances in the resistance box. So let me begin with 7 ohms in the resistance box. I find the balancing length to be 59.3 centimeters because for this position of the jockey, the galvanometer needle is showing 0 deflection. Similarly, you can find and tabulate the balancing lengths for 2 more values of resistances in the resistance box. After tabulating all the values, you can calculate the mean resistance of the first wire R1. Similarly, you can find the mean resistance of the second wire R2 by replacing this R1 with R2 in the right gap of the meter bridge. we connect the two wires end to end like this, we say that they are now connected in series. To find the effective resistance of this series combination, all we need to do is connect it to the right gap of the meter bridge and follow the same procedure which you used to find the unknown resistance for a single wire. Now to find the effective resistance of the same two wires in parallel combination, just connect their corresponding ends together like this. Now connect this to the right gap of the meter bridge and follow the same procedure which you used to find the unknown resistance of a single wire, and you will get the effective resistance of this parallel combination. Now that you have the theoretical and experimental values of the series and parallel combination, let us check whether they are matching or not.
Resistance wire R1 is connected in the right gap of the meter bridge. For a resistance of 7 ohm in the resistance box, the galvanometer shows null deflection when the jockey was at 59.3 centimeters. This length of the wire is the balancing length AD L centimeters. Therefore, length DC is equal to 100 minus L centimeter, which is 100 minus 59.3 centimeters. Therefore, length DC is equal to 40.7 centimeters. Unknown resistance R is equal to 7 into 40.7 by 59.3, that is 4.804 ohms. Similarly, the other observations when R1 is connected are as follows. Mean resistance R1 is equal to 4.818 ohms. The observations when R2 is connected in the right gap of the meter bridge are the mean resistance R2 is equal to 5.59 ohms. In the same way, the observations when both the wires R1 and R2 are connected in series are as follows. Mean resistance Rs is equal to 9.95 ohms. When R1 and R2 are connected in parallel, the observations are as follows. Mean resistance Rp is equal to 2.65 ohms. Resistance of wire R1 is equal to 4.818 ohms. Resistance of wire R2 is equal to 5.59 ohms. Theoretical value of effective resistance of R1 and R2 in series. Rs is equal to R1 plus R2. Rs is equal to 4.818 plus 5.59, which is 10.408 ohms. The experimental value of series resistance Rs, R1 and R2 in series. Rs is equal to 9.95 ohms. The difference of theoretical and experimental value in series, 10.408 minus 9.95, that is 0.458 ohms, is well within the experimental error. Thus, the law of series combination of resistances is verified. Theoretical value of effective resistance of R1 and R2 in parallel. Rp is equal to R1 R2 by R1 plus R2, which is 4.818 into 5.59 divided by 4.818 plus 5.59, that is 2.58 ohms. The experimental value of parallel resistance Rs. R1 and R2 in parallel is equal to 2.65 ohms. The difference of theoretical and experimental value in parallel is equal to minus 0.07 ohms is well within the experimental error. Thus, the law of parallel combination of resistances is verified. The connections should be neat, clean and tight. The connecting wire used should be thick copper wires and the insulation near their ends should be removed and rubbed with sandpaper. Appropriate range of the voltmeter and ammeter should be taken. If there is any zero error in the voltmeter or the ammeter, it should be corrected with the help of a screwdriver. The key should be inserted only while taking the observations to avoid the heating of resistance. Otherwise, its resistance will increase. The unknown resistance chosen should have high values in comparison with the internal resistances of the cells used.
I am sure that after watching this video, you have understood how to verify the laws of combination of resistances in series and parallel using a meter bridge. You are now ready to perform this experiment completely on your own without any assistance. Thank you for watching this video.